going to talk about local correctability in holography. This is loosely based on a paper posted a couple of months ago with Fernando Pestowski. We've been, for 20 years, living off of all the blessings that flow from ADS-CFT duality. And the subject entered a new phase about 10 years ago with the Ryu Takeyanagi discovery of the relationship between entanglement and geometry. But what was really kind of a game changer for me was the brilliant paper by Palmieri, Dong, and Harlow a couple of years ago, which emphasized that quantum error correction has a vital role in discussions of holography. There had been hints of this earlier, already in the late 90s, when people spoke of precursor operators. The idea was there that if you consider an operator deep in the vault, it's represented by a highly non-local operator on the boundary, which has the feature that the effects of that operator are invisible to local observers on the boundary. That's really quantum error correction. And later we recognized that black holes as fast scramblers are very efficient encoders of good error correcting codes. But what Palmieri, Dong, and Harlow emphasized and made a compelling case for is that there are aspects of holography which would otherwise be very puzzling, which are best understood in the language of quantum error correction. Beginning with Ryu Takeyanagi himself, because on first hearing it seems rather strange that we can equate entropy, entanglement entropy, which is not an observable, with area which is an observable. But they recognize that if you think of Ryu Takeyanagi as something that falls on a code subspace of a physical Hilbert space, that is less strange. Also, vault locality itself. If we consider operators deep in the vault, on a time slice, they should commute with one another, at least to a very good approximation, and yet they have overlapping supports on the boundary, so that commutivity may seem a little bit mysterious until you view it from the perspective that these operators are the logical operators of code which are acting on different logical subsystems and therefore naturally commute. And also, if you think about the reconstruction of bulk operators on the boundary, that's a highly ambiguous procedure. The same bulk operator can be represented on the boundary in multiple ways. It seems odd until you put it in the language that's very natural from the point of view of quantum error correction that different physical operators acting on the physical Hilbert space can act on the code space in the same way. Now they also emphasize that the right language for discussing these things is operator algebra quantum error correction. And there are several reasons why that's the right language, but one in particular is that this is the language we should use if we want to talk about superselection sectors in the logical Hilbert space, in the code space. And that's an appropriate thing to do in holography, where there are emergent gauge symmetries in the vault, as there should be in any theory of quantum gravity. Now, the subject of operator algebra quantum error correction came from quantum information, but it is perhaps underappreciated and underdeveloped. And what we were trying to do is to make a start on developing the subject further, and we made only a modest start on that so far. But the motivation is this, that someday we're going to throw away the crutch of ADS-CFT duality. We want to be able to stride with our heads held high through the splendors of de Sitter space, and that's going to require new ideas, and perhaps by thinking about geometry in terms of algebraic properties of codes, we can develop new perspectives that will at least give us hints on how to proceed. So let me start by saying a little about what I mean by correctability and how to think about Ryu Takiyanagi as a property of a code. And here I'm really following a lucid paper by Harlow that appeared last summer, or maybe the next 15 minutes. So first of all, if I have a quantum code, I want to keep track of the protected information. A handy way to do that is to have our encoded information purified by some suitable reference system. And then there's some encoding circuit, which I'll choose to be unitary by including in its input some number of qubits in a product state. And this circuit will then produce our code block. And now I would like to divide the code block into two subsystems, one of which I'll call A and the other complement, A complement. And I would like A to have the property that if A is erased, if it's discarded and we no longer have access to it, we can recover from that erasure. And that is what I mean by a correctable set of qubits in the code block. And that correctable set can be chosen in many ways, but suppose we consider some particular choice. So what I want is to be able to discard those qubits and then apply some recovery map, which can't touch A, which has already been discarded, and it can't touch the reference system, but it should restore the entanglement of the code block with the reference system and reassemble the code block in its original form. And the criterion for being able to do that was discussed by Fernando. One way of saying it is I can look at the marginal density operator of the reference system and the correctable set A, and it should factorize into a tensor product of the state and the density matrix on the reference system and the corresponding density operator on the state. In other words, on A, there should be no correlations between the two. If there were, then information about the logical system would have been lost to the environment when we discarded A. And we can see this condition is sufficient for us to be able to perform the erasure correction task, because what it says is, since the overall state is pure, that I should be able to identify two different subsystems contained in a complement, one of which purifies the reference system and one of which purifies the array set. So the encoding circuit should look like this. I can actually divide it up into two parts. There's some input entanglement. I don't want to call that A yet. Which will be shared by A and A complement. And I can divide the encoding circuit into a product of two unitaries. The boxes are unitary transformations. I might want to have some additional input qubits. And there's a unitary that acts on A and a unitary that acts on A complement. And once I draw the circuit this way, there are several things that are easy to see. One is that it's simple to correct the erasure of A. If A is discarded, then I can run this unitary circuit acting on A complement backward, and then I can throw away this part of the state which had been entangled with A, and then I can replace it with the entangled state, and then I can run the unitaries acting on A and A complement forward, and that way I'll restore the original state. Another thing that's evident is that if I want to perform any logical operation on the encoded system, I can do so without ever having to touch A. I can do it by running this part of the encoder that acts on A complement backward, then applying my logical operation to this logical system and then running the A complement encoder forward. So in order to apply a logical operation, I don't need access to A at all, or in other words, for any logical operation, there must be some equivalent one, which doesn't have any support on the correctable set. Another thing we can see is what the properties are of the entropy. In fact, we already know, because there are no correlations between R and A, that the entropy of RA is additive. But since the overall state is pure, this is the entropy of A complement. So the entropy of A complement consists of two pieces, one of which has to do with the entropy of the logical system, which in holography language I would call the bulk entanglement. And one has to do with the entanglement between A and its complement, which we could call the geometrical entanglement. That's the thing that's captured by the area in the Ryu-Takiyanagi formula. So if I thought about a holographic code, for example, and some particular cut on the boundary between A and A complement, there's some minimal cut through the bulk, and there's some entanglement associated with that minimal cut. So I can imagine preparing the state in the following way, introducing bell pairs along the cut, and then applying an encoding circuit, a holographic circuit, in which the cut it's really a product of two circuits. In one, the cut advances steadily through the bulk, picking up qubits as it goes, and eventually reaches A complement, and that's this part of the encoding circuit, and that will include incorporating some logical system, if there is one, which resides on the entanglement wedge of A complement, and another circuit which takes half of the entangled state and pushes it through the bulk to the other part of the boundary, A. So that's what's going on in a holographic code. And it's very natural to think of the entanglement as being the sum of these two pieces. We can make the story a little bit richer if we want to include logical information that can be reconstructed on both A and A complement. Now suppose I divide the logical system into two parts, each with its corresponding reference system, and I would like our encoder, again, to produce a physical code block which I can decompose as a product of two factors, where now I would like to be able to reconstruct the logical information that's purified by R on A, and likewise I would like to reconstruct the logical information that's purified by R prime on A complement. So the criterion, our task is really the same as before. We would like the, in order for that erasure to be possible, there should be no correlation between A and R prime, and no correlation between A complement and R. And so if we ask what that implies about the encoding circuit, now we'll have a picture that's similar to the one before, but now where there are two logical systems. And as before, it's easy to see that if, let's say, A is erased, and I'd like to be able to recover the logical system that's purified by R prime, I can do so by running this circuit backward, discarding this state which was entangled with A, replace it, and then run the encoding circuit forward. We can get the story to be even a little bit richer if we want to consider a decomposition of the code space into a sum of sectors. So if the code is equal to a direct sum of products, because there's some kind of super selection rule which restricts the operations that we can apply in the bulk on the logical system. Then I can just use a similar picture. But now I have a decomposition into sectors with a corresponding entangled state bridging A and A complement for each one of those sectors, and each one will have its corresponding purifying system. And so again, if I look at the entropy just for subsystem A, it will be the sum of a geometrical part and what we could call a bulk part. Well, the geometrical part has nothing to do with the logical system, but it's necessary in order for this to be a good code. But now it includes contributions from the entangled state in each sector that is entangled after the encoded circuit acts between the physical subsystems A and A complement. And now the bulk contribution will be a little bit more complicated than before because the bulk state will have some decomposition into sectors, and the bulk entropy will have one piece which just concerns the probability distribution governing how those sectors are weighted, and then an additional contribution which is a weighted sum of the entanglements in each one of the sectors. So this piece of the bulk entanglement is, in a sense, classical. It's not something that we can manipulate if we're restricted to performing operations in the bulk which preserve our decomposition into super selection sectors. But this part is actually distillable. So that by performing those physically allowed operations, we can extract a number of bell pairs shared between A and A complement, which is given by this expression. So just to be concrete, or a little bit more concrete, if we were to imagine a minimal cut in the bulk where there's some gauge invariant observable which can't be modified by operations except those that span the cut, like some electric flux flowing from one bulk region to the other, which we can change by applying local operators on one side or the other, then this is the quantity that would characterize how much entanglement we can distill. And all this was explained very beautifully in Daniel's paper. But now I want to talk about a somewhat more refined notion of correctability. Am I not staying high enough up on the board?
Well, sit down.
Which is local correctability. And to introduce it, let me remind you of something that we learned from the Ryu-Takayama formula if we consider just the geometrical part of the entanglement. Namely, I can consider looking at a boundary and dividing it up into subsystems, let's say A, B, and C, and then a complement of the three D, so that A, B, C, D consists of a whole boundary. And I might be interested in characterizing the entropy of the joint system consisting of the two disconnected components on the boundary, A and C. And there are two possible answers depending on which geodesics actually have the shorter length among the geodesics. I'm using the language appropriate for the Poincare disk, but similar statements could be made in higher dimensions. That the geodesics which separate AC from its complement could either look like this, or have a rainbow configuration like that. And if this is the right answer, then it means the entropy is additive. So in other words, there's no mutual information at all of A with C. And if this is the right answer, then SAC, which because the overall state is pure, is the same thing as SBD. And that would be given by the entropy of B plus the entropy of ABC. And those correspond to the lengths of the two geodesics. But again, because the overall state is pure, this is S of B plus S of D. So in other words, in this case, there's no mutual information between B and D. If we actually had some logical system in the bulk as well, let's say beyond the entanglement wedge of these regions, purified up here, then I could say something similar, except now this geodesic would correspond not to the entropy of D, but to the entropy of dr, because now I want to separate ABC from its complement, and that will also involve a contribution that comes from the minimal region that corresponds to that logical system in bulk. And so that would mean that it is the mutual information of B with dr which vanishes. So now, changing my notation a little bit, let's consider this more general question. That I have some code block which I... Sorry?
R is defined.
I couldn't.
I have not understood how R is.
Well, let's suppose there's a puncture in the bulk, and there are logical degrees of freedom which live on the puncture, and R purifies that system. And so let's suppose I have a code block which I can decompose as a product of three subsystems, A, B, and C. And what I would like to be able to do is to correct the erasure of A, but in this case, without actually having access to its entire complement, but just a portion of that complement. I would like to be able to apply an erasure correction map which maps B to AB, restoring the original state, but doesn't touch C, and of course doesn't touch R. But this is really the same task as before, but where now C is part of the system that we don't want to touch. And so the criterion is that we want B, mutual information of A with CR, to be equal to 0. In other words, the state of ACR should factorize. And then the circuit that we can construct that encodes the state has a structure that looks like this. Where this would be system A, this is B, and this is C. and there are two purifying systems associated with B and C. Now the point is that, again, that it must be, since the overall state is pure, that system B contains subsystems, one of which purifies A, and one of which purifies CR.
So why did you have to draw D in that picture if you say you have a pure state?
Do I have to draw what?
D.
Well, I'm sorry, I changed my notation. There's no D anymore.
Oh, okay.
Right. So what I'm now calling the system that I'm now calling B corresponded to AC here, and B is the system that's being erased.
Oh, okay.
Yeah.
All right.
I don't know. There's a clash between alphabetical conventions. So now, of course, the point is that we can discard A. And now, in order to recover the original state, it will suffice to run the encoding circuit for B backwards, and then discard this part of the state and replace it with the entangled state, and then run the encoding circuit for A and B forward, but there will be no need to touch C. So coming back to the ADS, or the Poincare disk version of this problem, now I have a region that there's a ratio I'll want to correct, which I'll call A. There's a system which consists of two connected components, let's call them B1 and B2. And then there's a complementary system on the boundary. And in order for this to actually be the minimal geodesic, which separates B1, B2 from its complement, we'll want the length of the minimal geodesics associated with A and with AB to be less than the sum of minimal geodesics for B1 and B2. And since the length of the minimal geodesics goes like the log of the size of the boundary region, I can translate that into the statement that the size of A times the size of AB should be less than or equal to the size of B1 times the size of B2. And so that's some quadratic condition to be solved. And the conclusion is, let's say B1 and B2 are equal size, that we want the size of B1 over the size of AB to be greater than the square root of 2 minus 1. That is about 414. So the point is that if we puncture a hole in the boundary and we would like to recover from the erasure of that portion of the boundary, we don't need access to the whole boundary, but just some sufficiently large region surrounding the part that we've erased. And it is larger than the erased part by a multiplicative factor, which is about a factor of 5.8. That's what I mean by local correctability. And it is a manifestation of the entanglement structure of the boundary state, namely that it has limited long-range entanglement. So in order to restore the correlations, I don't have to reach so far beyond the erased region. Now, one of the things that I thought was interesting about the Stanford paper, the Hayden et al. Paper on constructing holographic codes from random tensor network instructions is that one could give a nice geometrical interpretation to the entanglement on the boundary for general graphs. So in other words, we could consider geometries which are not necessarily negatively curved This local correctability in this case, and the locality of the boundary state, has to do with the negative curvature in the bulk. But we can consider more general geometries and still apply Ryu-Takeyanagi type reasoning to understand the entanglement structure. And to give an extreme example, we could imagine, for example, having a hemispherical cap where I consider the hemisphere to be the boundary and the top half of the sphere to be the bulk. And now if I consider some region along the boundary, some region A, since the geodesics on the hemisphere are great circles, the shortest path connecting together the two endpoints of the orange region, if that region is sufficiently small, will just be A itself. And so the entanglement will obey a volume law. It will rise linearly with the size of A until A reaches more than halfway around the hemisphere, in which case the shortest path will be completing the equator. And so we would have a picture for the entanglement of A with its complement as a function of the size of A, which looks like a page curve, rising linearly until A is half of the boundary and then going back down to 0. If we have a number of encoded qubits n on the boundary, once we get past n/2, the entanglement starts to come down again. And so this is a state which has much longer range entanglement than the holographic state. We don't really have local correctability. We really do need more than half of the state if we're going to be able to correct. And correspondingly, if we had some logical system that until we have more than half of the boundary, we have no ability to recover the logical information. It's not until we get just over half the boundary that we can recover the system that purifies the reference system. So you can think of this as a kind of geometrically local circuit, but it has a size given by the volume of the hemisphere, which goes like n squared if there are n qubits on the boundary. So it actually has the properties that I described so far, which would hold if we had a Haar random encoding, but it also holds for unitary 2 design. And we can think of this circuit as one which is encoding that unitary 2 design, and therefore providing a good code with long-range entanglement. But that's not what happens in holography. Now in our paper, Fernando and I emphasized that we can get interesting information about the structure of the logical system by studying what we call the distance and the price for different logical subalgebras, of the logical system. Well, distance is a familiar notion in coding theory, but here we want to apply it to any possible subalgebra of the logical system, and it just means the size of the smallest set of non-correctable with respect to that logical. I hope my holographic aid looks different from my Latin aid. It's supposed to be an algebra. This one really doesn't look different. By the price, which is a less familiar notion, but a very natural one, we mean the size of the smallest set of qubits in the block that support the algebra. That is such that for every logical operator in the algebra A, we can find some logically equivalent operator acting on the code space in the same way, which has support only on some set. And we want to choose the smallest set for which all of the logical operators are supported in that sense. So having a big distance is good from the point of view of wanting to protect the logical system. It means you have good erasure protection. Having a large price is in a way bad if your goal is to be able to manipulate the logical system or reconstruct it. You won't be able to apply non-trivial logical operations until you get a hold of a number of qubits, which is given by the price. And in fact, if the algebra is non-abelian, then the price must be at least as large as the distance, because a region that supports a non-abelian algebra is necessarily non-correctable. Now, if the price is comparable to the distance, or equal to the distance, that's the kind of feature we would have if we could think of the system in the bulk, if we want to give it a geometrical interpretation, as being very well localized in the bulk. So that means that, for example, if I had a point in the bulk, and if I have a non-correctable set, which encompasses the logical system in its entanglement wedge at that point in the bulk, because it's just a point, once the set becomes non-correctable, it also allows us to reconstruct the algebra. So price equals distance is sort of an algebraic way of describing what we mean by having a point in the bulk. And we would like to try to extract other lessons about how to think about geometry in kind of an algebraic way. Now, coming back to the Poincare disk, we could ask about the distance and the price in that case. So, for example, I might have some non-correctable set A on the boundary, meaning that there is some logical system which is purified by a reference system which is contained within its entanglement wedge. But now I would like to slice up region A to the minimal set from which I can reconstruct that logical algebra, or which has the property of being non-correctable. And now, because of the local correctability, we can make the observation that we can cut a piece out of region A without altering how far the entanglement wedge reaches into the bulk. Because for this diminished region, just consisting of this connected component union with this one, the minimal geodesic is just this rainbow configuration, and so it remains non-correctable. And then we can proceed in that way, taking the disconnected region that remains and punch further holes out of it, punch a hole out of the middle of this region and this region, but it remains non-correctable, and then punch a hole out of this region, this region, this region, and this region, and so on. Carrying out the procedure recursively, each time reducing the number of qubits in the set that supports the algebra or is non-correctable. So when does that procedure end? If we imagine we have a regulator, so we have some finite number of qubits on the boundary, there's some lattice spacing on the boundary. If we carry out this procedure for m rounds, then after that we will have 2 to the m connected components each of which will have a size which is x to the m times the original size of A, where the connected components that remain each time I perform one of these sets is reduced in size by the factor x. And the procedure will halt when we finally reach having just one site inside each region. And then we have 2 to the m sites because we have 2 to the m regions, each of which contains a site. And so the distance will be bounded above by 2 to the m. But I can write that as the size of the original region expressed in latticed units raised to a power. And that power will just be log 2 divided by log 1 over x. And in the case of using a Ryu-Takayanagi formula on the point for a sphere, then x was just the square root of 2 minus 1. And so this turns out to be a number which is about 0.786. And a similar statement applies to the price of some algebra which is deep in the bulk. In fact, we can consider a situation like this, where we have a Poincare disk. We cut out a puncture. We think of a logical system which is residing at that inner boundary. We find a region whose entanglement wedge contains that central region, and then proceed to convolve recursively, as I described, until we're left with isolated sites. And so the price also will obey a similar scaling law. And we can think of the size of the original region as a measure of how far radially inward we have to go to hit the puncture. So this quantity, A...
Are you reconstructing a region of size RADS?
I'm reconstructing a region which can be much larger than the ADS
No,
scale.
but I'm curious about the opposite. So
Oh, you mean what happens if I do that?
Because we usually think of that as a single lattice site of n squared degrees of freedom.
Oh, I see. Right, so I guess I'm being agnostic about that, but you're right that this site, since I'm representing the boundary by a lattice, will be a high-dimensional object because we have, a non-local structure at the ADS scale. Yeah. But the statement about the scaling will still hold, that the distance or the price will scale like, we can think of this as actually the ratio between the total size of the code block, which is the radius of the outer boundary divided by the radius of the inner boundary, which is the number of encoded objects that reside there. And so the distance and the price will be bounded by something that goes like n over k to the alpha. So we call this Uber holography. So eventually we want to understand situations in which the number of emergent, 2 minutes left, in which the number of emergent dimensions is greater than just 1. And here we have kind of a baby version of that, because we have a region on the boundary which has some fractal dimension, which is less than 1. And from it, or upon it, we can completely reconstruct this bulk logical algebra. And so it is sort of hidden into the local correctability of the ADS CFT construction that this is possible, that you can chop down the supporting set for the algebra to something that is lower dimensional than you might have naively expected. Well, the last notion I was going to discuss, but Adam says I have 1 minute left, was approximate correctability and approximate local correctability. So I won't be able to say much about that. But the point is, and this came up both in Fernando's talk and in Brian's, is that our criteria for local correctability and for correctability will not be precisely satisfied in a conformal field theory, for example, where we do have correlations at long distances which are algebraically decaying but can be approximately satisfied. And that will suffice for being able to correct the erasure or do reconstruction with fidelity which is close to 1. And so we can try to study that in a system which has the kind of long-range correlations that a CFT does, namely in MERA. And that's what Kim and Castoriano did in a recent paper. This idea of local correctability has been, when approximate, has been discussed in several recent papers, one by Flamy et al., one by Kim and Castoriano, and one by Hestowski et al. And, well, one thing we can say is this, that if we have some region on the boundary and some logical system which is beyond its naive entanglement wedge, that as you might anticipate, this logical system, if encoded by a mirror on the boundary, will have spread out to a region which is much larger than A by an amount which is exponential in the reach into the bulk beyond the peak of the entanglement wedge of A, where this logical system lives. And so if we compute the mutual information of R and A, it will, aside from some prefactor, scale like 2 to the minus nu, where nu is some scale dimension of a scale invariant mirror, the distance in the bulk where the logical system is inserted minus a log of the size of the region A. And we can also say something about local correctability, where now we have this picture again, where B1 and B2 are padding the region whose erasure we want to be able to correct. And as we apply entanglement renormalization through multiple rounds, region A will eventually shrink to a point. And if that happens before regions B1 and B2 shrink to a point, then we continue to apply entanglement renormalization and get an exponentially suppressed contribution to the mutual information now of but now the number of rounds we'll be able to do of entanglement renormalization will be limited by the size of B. So we'll get something like 2 to the minus nu times the log of B, log of B1, say, minus the log of A. Or in other words, that's just the size of A divided by the size of B1 raised to a power. So formally, if we consider this scale dimension to be large, this is similar to the Uber holography scenario I described. That is, we can continue to hollow out regions inside, but the scale dimension is different because now AB is larger than B2 by a factor of 3 instead of the factor that I found before. In fact, this scheme looks more local than what we infer from the RT formula applied to the Poincare disk. In other words, we can do the local correctability without reaching out as far beyond the region A, which has been erased. So the entanglement is less long range than we would get from the RT formula. I'm not quite sure what to make of that discrepancy. On the one hand, Miro doesn't quite capture the geometry of the Poincare disk. On the other hand, you might have thought Miro would describe pretty well the correlations within a boundary CFT. So I'm sorry I've gone a little bit over time, but the main thing that we're trying to do, again, is this, that there are a lot of things we still don't understand, even about ADS CFT, but eventually we want to go further. And I'm suggesting that if we think about the structure of subalgebras of a code subspace and give them some kind of geometrical interpretation that may give us guidance about how to extend holography to new settings. Okay.